In this lecture, we will learn about biodegradable polymers. We have learned what is the importance of biodegradable polymers in the earlier lectures. So, in this particular lecture, we will concentrate on what are the biodegradable polymers which are currently available. And as well, we have also learned about the biodegradation part, that what are the different terminologies that have been basically utilized by the engineers and scientists to describe the degradation part. So, one can be biodegradation, that requires basically an enzymatic activity or a microbe activity to cause the degradation, or it can also be bioerosion, in which case the bio is a combination of physical plus chemical activity to cause the degradation of a particular polymer, or otherwise it can also be bioresorption or bioabsorption, in which the component is basically being degraded by the cellular activity such as phagocytosis. So, in this case we can see it is the biodegradation, it is either by enzyme or microbe. Bioerosion is basically being component, or it can again be the breaking of the overall chain by a certain cellular activity, that is being called as a bioresorption or the bioabsorption, and all these things are happening within certain biological environment. So, those are the other terminologies which we have utilized earlier in terms of defining the biodegradation. And earlier the first of all, the developments which have been initially the way it was started in terms of defining materials, it started all with defining certain stable materials, because once we are implanting something into the body, probably we learned that probably we need to have some material which is stable under extreme environments, which is the body fluid environment, and it should be able to sustain there for a very prolonged time. So, that was the earlier mentality, but later on now we have realized that that particular material can also impart certain functionality. It can allow the precipitation of a new cells or new bone around the damaged area. So recently the focus has also been on developing certain biomaterials. So, early developments were basically on exploring the stable materials, and there are many polymers which are available which are highly stable under the biological environment, and they are virtually non-destructible. Certain examples are Teflon, Kevlar, or polyether ether ketone, so PEEK. So, there are certain materials such as Teflon, Kevlar, and polyether ether ketone, which are basically very stable for a prolonged duration of time, even under severe biological conditions. So, they become generally non-destructible. So, recently this term of degradation or the degradable polymers has come into the picture, because we can impart certain functionality without causing any deleterious effect to the bone. In case we have a material which has been implanted permanently into the body and which does not degrade at all, which remains there for a prolonged time, that will cause certain the shielding of the stress shielding, and in the process the new bone formation will basically be hindered. So, in that case we want the material to get dissolved into the body, so that functionality can be taken up by the new forming bone, and the bone really stays there for a new bone really starts growing in the damaged area. So that is the reason the research has been now targeted more on developing of certain degradable materials. And again there is only a limited research has been done, so we have only limited number of available degradable materials. Why that is there? Because it requires challenges in design. First of all, as soon as the material is being implanted into the body and it is a degradable polymer, first challenge is the design part, because how the dissolution will affect the overall integrity of the structure in entirety. So, if I am implanting certain biodegradable polymer and with time it starts to dissolve, then we need to know exact mechanism of how it is dissolving at exact time when it will get dissolved. So, for that it requires certain challenges in design in terms of synthesizing new degradable biomaterials, and at the same time it is very important in terms of the tissue engineering as well, because once a material is being implanted, it has to be taken over by certain tissues, the healthy tissues, which can reduce the overall damage area. So, in that particular case we need to have a particular material which is properly designed or properly engineered to yield a controlled cellular response, and that also should be predeterminable. So, we need to develop certain material which can have a predetermined dissolution rate, and as well as the cellular or the tissue engineering or the cellular response rate as soon as the material is getting dissolved. So, that is what we can see in terms of development, that the early development was done basically on the stable materials, and we have certain many materials which are available which are highly resistant to the biological attack. Those are polyether ether ketone, Teflon, Kevlar, and many other. And again, the development of degradable biomaterials, it is a new research area, because it requires so many technicalities in terms of designing the material, in terms of determining their dissolution rate, and again in terms of their controlled cellular response, how the cells will respond to the particular implanted degradable polymer. So it introduces much more of a complexity in terms of designing this degradable polymers, and that is how the new research is basically being targeted onto. And as we discussed, that there are certain stable materials which are Teflon, Kevlar or PEK, which have been basically available, but over the past decade there has been much more research on resorbable biomaterials which can basically be dissolved hydrolytically. So we have some hydrolytically unstable material, hydrolytically unstable material that can basically degrade, and then we can perform some toxicological studies on them, and then we can basically develop certain new materials from which we can decide the mechanism of their dissolution. We can decide the overall their temporal stability, at what rate they will dissolve, and what is the cellular response to that particular developed new biomaterial. So those are the certain complexities which we need to basically develop, and therefore there are many stringent requirements onto them. So they can come up in terms of toxic contamination. In case the one polymer is getting degraded, it should not render any toxic ingredients into the body. So while leaching, it should be become monomer, and it should be basically get stabilized. It can also form some emulsifiers, initiators. So there are many entities which basically comprise of polymers, such as monomers, stabilizers, emulsifiers or initiators, which are made to engineer a particular polymer in terms of making it biodegradable. So we need certain stabilizers, so that keep the material stabilized enough for a long time, emulsifiers, initiators to initiate the particular reaction or the polymerization. So there are many ingredients which are there in a engineered polymeric material, and once they are being degraded into the body, they should be free of toxic excretion. So that's what is being the one of the challenges which we can really get. And again, the degradation products or metabolites which are there in a polymer, they should not again be contaminating, or they should not cause any adverse effects to the body or to themselves. So that is again one more challenging requirement for engineering a degradable material. And again, after that, all that it needs to undergo certain clinical first of all in vitro studies that basically confirms that the material is biocompatible or cytocompatible. Then again it has to undergo certain in vivo studies, and then it should be also undergo clinical trials, and there are again phase 1, phase 2 types of clinical trials, and then it has to be approved by Food and Drug Administration. So there are so many stringent requirements that whatever materials which have been developed earlier, they continue to be the dominating biodegradable polymers, because there are so many impositions. Like first of all, material has to take very stringent requirements of design, then control, and then again through in vitro, in vivo, and then clinical trials. It is such a lengthy and complicated process, and again there are certain stringent requirements that they have to possess so and so in terms of mechanical, in terms of biological criteria. So they are very stringent requirements which are being imposed by the Food and Drug Administration. So currently basically there are only 3 synthetic polymers which are currently or which are very routinely used, and it becomes very hard to develop certain new biomaterials, though we have other biomaterials, but the exact proven clinical cytocompatibility is I think still under investigation. So we have polylactic acid, polyglycolic acid and polydioxanone. So this is the overall structure of the polyglycolic acid. It's again a ketone, and again we have it's an COOH bond, so we have a polyglycolic acid, and then again we have a polylactic acid, and then we have polydioxanone. So these are certain available polymers which are routinely used as the biodegradable polymers, though we have certain stable polymers of such as Teflon, Kevlar and PEEK. And then we can in terms of developing the degradable materials, they have to undergo very stringent requirements of basically being posed as good ingredients, such as the toxic contaminant should be absent while the material is being leached out. So even the monomers, stabilizers, emulsifiers or even the initiators, they have to be free from any toxic ingredient. Then the degradation part of it also should make it much more stable. Even the metabolites should not be toxic, and they have to be approved after the in vitro studies, in vivo studies, and again by the clinical trials to make it approved by the Food and Drug Administration. And currently there are only three polymers which are basically being routinely used, which are polylactic acid, polyglycolic acid and polydioxanone. Why? Because initially when the development has occurred, these materials have come out as one of the established practices of utilizing all these three materials as biodegradable polymers in such as sutures or maybe a wound closure. So they have retained as one of the primary users because it has now become so difficult to get the new biomaterial approved by the Food and Drug Administration in terms of undergoing stringent design and all such requirements. And currently there are many materials which are available, the polymeric biodegradable materials which are available. So first of all, one is polyhydroxybutyrate, which is also called PHP or polyhydroxyvalerate. And again these are bioerodible polyester. It means they basically are getting they are basically being converted from the biosoluble form to bioinsoluble water insoluble form to the water soluble form after undergoing certain microbial activity, and then again they are derived from the microorganisms, and so that is what that is what these polymers are, polyhydroxybutyrate. And again the copolymer of 30% 3-hydroxyvaleric acid and rest polyhydroxybutyrate, it is now commercially available as a polymer, biodegradable polymer, which is called biopol. And they also serve as a intercellular storage, basically because they have excess energy and carbon available with them. So that is how they are basically being utilized as a biodegradable polymers. So in this case we can see that it is and again the PHP is one of the crystalline materials, and it is little brittle in nature, whereas the combination of polyhydroxyvalerate and polyhydroxybutyrate, so this is more crystalline in nature, and then this one basically makes it more flexible. And in this case we can see there is a combination which is now available by the copolymerization, because it is much more crystalline, this is much more flexible. So it is now available as a commercially available copolymer of known as biopol. So it is that is what is available as here. And again we can see that the copolymer, it can also be degraded by the soil bacteria. So the degradation part also is very easily attainable in this particular case. And again by the combination of PHB and PHV, so the polyhydroxy butyrate and polyhydroxyvalerate, this polymer can be engineered in such a manner that the degradation rate can be easily controlled. So by a particular combination of PHP and PHV, we can control the rate of degradation, and hence we can utilize them as a controlled way of in engineering a particular structural material, that as soon as this material is getting degraded, it is being taken up by the surrounding cell to retain the strength. And again PHP is one of the biocompatible copolymers, copolymer. Why? Because it degrades to a D3 type hydroxybutyric acid, and which basically is nothing but a constituent of the human blood. So that is the reason this PHP, it shows a very low toxicity. So in this case we can see that PHP, once it is getting degraded, it is degrading to the D3 hydroxybutyric acid, and which essentially is the constituent of the human blood, and that is the reason it shows a low toxicity. And as we know, as we have talked earlier, that PHP, it is this homopolymer is much more crystalline and brittle. So that is the reason we want to add some flexibility so that we can easily process the material, and that is how we used the polyhydroxyvalerate polymer, and this copolymer is now becomes much more flexible and processable. And because of that, once we have this copolymer, and if we can control the degradation rate, because by allowing a proper combination of PHB and PHV, we can allow easy control release of the drug. And now once we can retain the strength by increasing the PHP content, because it is much more crystalline, we can also utilize in sutures which can sustain for a little longer time. Generally some sutures, they degrade in 2 to 3 weeks. So in this case, if we want to retain the sutures for a little longer time, we can allow a proper combination of PHP and PHV, and somehow we can control the strength of those sutures for a prolonged time. We can also utilize them for the artificial skin, or even for paramedical disposables. So in case of certain industrial applications, we can also utilize them for some paramedical disposables. So we can see that copolymer becomes much more boon in terms of controlling the drug release rate, in terms of deciding a particular combination of PHV and PHV. We can also decide the overall strength which can be retained by the sutures for a prolonged time, or we can also utilize them as artificial skin, or also for the paramedical disposables in case we want to seal certain chemicals and all, and we can basically being able to dispose it after its usage. So these copolymers come as a rescuers in terms of all such applications. So that is the overall advantage of utilizing the PHV and PHB. PHB is the polyhydroxybutyrate, which is highly crystalline, but it is very brittle. That is the reason we add PHV to it, that is polyhydroxyvalerate, and by combination of them we can always control the overall degradation rate, and again they can also be degraded by the soil bacteria. So that is the overall thing about the PHV and PHV copolymers. The second class is the polycaprolactone, and polycaprolactone, it's a semi-crystalline polymer. Like in PHB we had much more crystallinity. In polycaprolactone it is semi-crystalline polymer, and again it can be degraded by certain microorganisms, and it has a very high solubility and it has a low melting point. And since it is highly soluble in certain organic compounds and it has a low melting point, it basically eases out the processing part, that we can easily process the material, because once we can easily solubilize, we can make a solution of this polycaprolactone, and then we can process at much lower temperatures, and because its melting point is only 59 to 64, so we can attain very high fluidity even at say 100 degrees centigrade. And now that makes the material very processable, that we can easily cast into certain shapes, we can compression mold it to any certain complicated shape. And again the advantage of this one is again that it can degrade at a slower pace than PLA, and so that we can devise certain drug delivery systems which can sustain for a much longer time. So if we have polycaprolactone, we can design the drug release rate in such a manner that the drug release rate can be particularly controlled, but the system will remain in the body for a prolonged time because it has a lower degradation rate than that of a PLA. So again there are certain clinical trials which have already been done, phase 1 and phase 2, and they are now commercially available, and they are mainly utilized for the wound closures as well. So this is the overall structure of the polycaprolactone, that these are the semi-crystalline polymers, and because of their high solubility and low melting point they become highly processable, but because of its lower degradation rate in comparison to that of a PLA or the polylactic acid, we can induce certain long-term drug delivery devices into the body, and now they can render the drug for a very long duration of time. In case we need extended drug delivery, drug release in certain cases, we can basically attain that using polycaprolactone, and they have successfully completed the phase 1 and phase 2 easily. So that is what is basically being utilized for the polycaprolactone out here. And again there are certain second classes of material, and then which are called polyanhydrides. And again initially polyanhydrides, they were once they were being developed for a substitute in the textile application. So that is what the initial exploration of this polyanhydrides had started, that they were being substitute for the polyesters, so that they can make out a new textile material out of this polyanhydrides. But eventually with time they have failed because they have low stability, low hydrolytic stability. So they become highly unstable in presence of hydrolytic conditions. So they basically had failed as a textile material or as a replacement for the polyester. But now eventually that started or triggered the development of these polyanhydrides as a bioabsorbable or the biodegradable materials. And again we can see that the polyanhydrides, they are very specific in terms that the aliphatic polyanhydrides, they can degrade within days, whereas the aromatic polyanhydrides, they degrade over several years. So we can see that we have a certain window available with us, that aliphatic polyanhydrides, they will degrade within couple of days, whereas we have the aromatic polyanhydrides, they will degrade within certain or over several years. So we can develop or decide as a particular range in which we can use these materials or as a degradable materials in terms of certain healing. So if you have certain wounds and all that, we can always decide a particular scaffold which will degrade slowly or at a rapid rate. So depending on how severe the particular injury is, we can always devise a combination of these polyanhydrides, whether we want them to degrade either in days or in years. So now this gives a better control in terms of engineering this particular degradation. So we can see that we have certain anhydrides which are available with us commercially, which are called PPSA anhydrides. So we have very complicated anhydrides which are available with us. So these can be either aliphatic, or this can again be aromatic. So which can be, through which we can really control the overall degradation which is happening on the anhydrides. And as we know that these anhydrides were developed being as a replacement for polyester, so that they can be used in the textile industry, but because of their low stability under hydrolytic conditions, so they became highly unstable, or they have failed as to emerge as a replacement material for the polyester. But now they have been ventured into developing certain degradable polymers, and now we can see the degradation rate is being governed by the overall structure or the overall manner in which the particular polyhydride is constructed. If they are aliphatic, they can degrade within couple of days. If they are aromatic, they take a couple of years to basically degrade, and that provides a better control in terms of engineering this polyanhydride as a biodegradable polymer. And again, the problem with that problem or the advantage with this polyanhydrides is they are among the most reactive and hydrolytically unstable polymers. So though we say that the polyanhydrides, they can be ranged within couple of days to couple of years of degradation, they are one of the very reactive and hydrolytically unstable polymers. So they have both advantages as well as disadvantages. First of all, the advantage part that they suffer very high rate of degradation, and because of the surface erosion. So they do not need any external catalyst or excipients for the release of the drug. So in one case, we can induce a very high rate of drug release without any external catalyst or excipients, and still they will suffer very high rate of degradation just by engineering the combination of aliphatic or the aromatic polyanhydrides. But at the same time, because of their high reactivity, they can also start reacting with the drug itself, which is being released into the body. So they tend to react with the amino group or nucleophilic functional group, and when the material is being processed, because the processing has to be done to mix the drug with the polyanhydride, and the processing has to be done at little higher temperature, so that it is above the melting temperature of the polyanhydride, and during that particular process it starts to react with the amino or the nucleophilic functional group, and that basically limits the drug which can be easily incorporated with the polyanhydrides. So we realize that in this particular polyanhydride we have both advantages as well as disadvantages, that it is one of the most reactive and hydrolytically unstable material, and because of that it has the advantage that it does not need any external excipient or the catalyst in terms of degrading itself. So that it can easily occur by the surface erosion, and it can also evolve drug delivery without any external agents, but at the same time it limits the kind of drug which can be utilized in this polyanhydride, because for a high temperature processing they tend to react with the amino group or the functional nucleophilic group of the drug itself. So that creates a problem. So that limits the overall drug which can be utilized with the polyanhydrides. And again, polyanhydride, they have shown to possess excellent in vivo biocompatibility, because they have the structure which is similar to the byproducts or the breakage products of this polyanhydrides. They are not really toxic, and the drug loaded devices, which are drug loaded devices of polyanhydrides, they can be easily processed by the compression molding or by micro encapsulation. So we can easily process these particular materials using certain drugs by using compression molding or the micro encapsulation, and again it has shown to release either insulin or bovine growth factors or angiogenesis inhibitors such as heparin or cortisone, or certain enzymes such as alkaline phosphatase or beta galactosidase, which has been successfully incorporated into the polyanhydrides, and the release of these particular enzymes or drugs, they have been successfully being characterized or being evaluated by the researchers. And one of the essential application of polyanhydride is in the brain cancer treatment, and that the delivery of this BCNU, that is bischloroethylene nitrosourea, which is being utilized for treating the brain cancer, and that is being successfully being tested using this polyanhydrides. So that is one of the very essential applications of this polyanhydrides. So people have seen that, researchers have seen that polyanhydride, they have very exceptional in vivo biocompatibility, And the advantage of these polyanhydrides is that they can be easily processed by either compression molding or by micro encapsulation, so that they can be easily utilized in terms of delivering either the insulin or certain enzymes or angiogenesis inhibitors, or they can basically also treat the brain cancer by release of this BCNU particular chemical for treatment of the brain cancer. So that is the overall advantage of this polyanhydrides, that they have they are hydrolytically very unstable, and they are highly reactive as well. So they don't need really any external agents to release the chemicals or the drugs, and they have shown exceptional or excellent in vivo cytocompatibility, and they can be easily incorporated with certain drugs, insulins, enzymes, or the bovine growth factors, which can be easily incorporated into the polyanhydrides, and they have shown controlled release rate of all these chemicals or drugs. And the next class of the biodegradable polymers is called polyorthoesters, and they are basically the synthetic degradable polymers which are being formulated to undergo certain surface erosion. So in this particular case, the water insoluble chemical is now being converted to the water soluble product by both chemical as well as physiological actions under biological conditions. And in this particular case, a slab-like device is basically being embedded into a particular polymer, and that starts releasing a drug. So that is now releasing the drug at a very controlled or a constant rate. So in this particular case, we have polyorthoesters. They are synthetically degradable polymers, and they undergo surface erosion. So the combination of both physical as well as the chemical activity under biological conditions, it starts degrading this particular polymer, and these slab-like devices are being placed which are embedded in the polymer, and the degradation of this polymer starts releasing the drug at a very constant rate, and they have been basically utilized for delivery of either steroids or cyclobenzaprine in this particular case. So that's what we see in the polyorthoesters. They are degradable polymers, and they are being now designed or formulated to undergo surface erosion. And now the slab-like devices, they are being encapsulated in a polymer, which are embedded in a polymer, and that polymer degradation starts releasing the drug at a very constant rate, and they have shown to be very good for certain steroids and cyclobenzaprine. So that is what the overall deal with the polyorthoesters, that they can provide a controlled release or the controlled release of the drug at a very constant rate. So that is the advantage with the polyorthoesters, and here is the overall structure of the orthoesters. We can see that DETOSU 16HTT CDM orthoesters, which are now being shown here. So we have the DETOSU and TCDM part here, and the 160 HD part out here. So that is what is being shown by the polyorthoesters, that they can provide a very controlled or a constant drug release rate as the slab-like devices are being encapsulated in this particular polymeric material. And there are again certain other class of materials which are called polyamino acids, and obviously this also terms as the pseudo polyamino acids, and obviously proteins are being composed of amino acids. So the first intuition which comes out to us is, oh, why don't we use them as a controlled degradable materials? So polyamino acids, they have essentially come out of this particular intuition, or the first action, that they are also amino acids, and the degradation of this particular amino acid should not be toxic at all. So as we know that proteins are also made up of amino acids, so thus these polyamino acids or the pseudo polyamino acids, they become the candidate materials for the biodegradable polymers. And the advantage with them is that we can have the side chains. We can always attach certain drugs to it. So first of all, they form the basic nature of the proteins, the basic chain of proteins. It is nothing but the amino acids, and then amino acids, we can attach some sites on the side chains. We can always attach certain drugs, and again on the cross-linking agent or the pendant group, we can always modify the physiomechanical properties of the polymer. So depending on how do we cross-link this particular amino acid, we can always alter or tailor the physiomechanical properties of the polymer itself. So on first hand, on the side chains, we can always attach certain drugs, and secondly, we can always alter the cross-linking properties, and then from that we can always alter the physiomechanical properties of polymer itself. So we have both the advantages of either altering the mechanical properties or altering the chemical properties which are required for the drug delivery. So the overall combination of these two can result a very nice combination. That is what being utilized as a for the polyamino acids. And again, for them being the basic chain of the proteins, they show a very low level of toxicity because the degradation is to the natural amino acids. So that is the advantage with the polyamino acids, that first of all the overall philosophy is that proteins are made up of amino acids, and then now these amino acids, they basically become the first users, the first thought basically comes is that these amino acids now can become an inherent part of the protein itself, and they can degrade to a very non-toxic ingredients. And again, on the side chains we can always attach certain drugs. At the same time we can play with the cross linking, and then we can again define the physiomechanical properties of the polymer itself. And again, the degradation of this polyamino acid can be to the can become to the natural amino acids, and then they can show a very low level of toxicity. So that is the advantage with the polyamino acids. Again, the applicability of polyamino acids, it has been to suture materials. It can also provide artificial skin substitutes or drug delivery. The advantage with the polyamino acids is since we can play with the mechanical property or the physiomechanical properties, we can basically design a suture which can sustain its mechanical strength for a little longer time, or to the time at which we want it to retain. Generally sutures, they are highly degradable and they tend to degrade within very short time. So that is the advantage with the polyamino acid, that we can design certain suture materials which can sustain the strength for a little longer time. They can also be utilized as a artificial skin substitutes. So in that particular case, we want the strength or the degradation to occur as soon as the new skin is developing. Again, we can also provide a controlled drug delivery using this polyamino acids, deciding on its either the drug on the drug part from the side chains, or the physiomechanical properties of utilizing the cross linking. And again, they are highly insoluble, but the problem with them is they are highly insoluble in organic compounds, and again they become also non-processable. And again, they have problems of that that they tend to swell a lot in an aqueous media, and once they are swelling, it becomes hard to basically interpret what will be their overall dissolution rate or a drug release rate. So that is the problem with them, that they are highly insoluble, and again they have that makes them non-processable, they don't become easily processable, and again they have tendency to swell once they come in contact with aqueous media, and once they swell, then it becomes very hard to predict what will be the overall drug release rate in the polyamino acid. That has basically limited the overall applicability of this polyamino acids. And again, it has one more problem, that that in case we have because of the cause of antigenicity of this polyamino acid, because when it contains 3 or more types of amino acids, so that basically excludes them as a potential potential biomedical applications. So though they have been used as suture material, artificial skin substrate, or the drug delivery, their antigenicity when we have amino acids of 3 or more being contained by the polymer, so that creates a problem in terms of an antigenicity, and that basically excludes their biomedical application. Again, they don't have any controlled drug release rate because they tend to swell, and once they are swollen, it becomes hard to predict the overall degradation rate, and that basically limits the overall predictability in terms of characterizing or quantifying what will be the overall drug release into the body. And again, their insolubility and the non-processability, it basically has limited the overall application of polyamino acids as the biodegradable polymers. The next class of biodegradable polymers is the polycyanoacrylates, and they have been basically utilized as bioadhesives, and because they form potential drug delivery matrices. But again, they have problem that they tend to induce a significant inflammatory response once they have been implanted. So they tend to create some inflammation at the implantation site, and that is basically limited the use of polycyanoacrylates as a degradable implants. So though polycyanoacrylates have been utilized as bioadhesives, they tend to basically cause inflammation at the implantation site, and they tend to form very potential drug delivery matrices, but because of inflammation, their overall usage has been limited limited as a biodegradable implant. Then again, there is the next class of biodegradable polymers, which is polyphosphosphazines, and again this is made up of the nitrogen phosphorus bond, and those form the overall backbone of this particular polymer, and they generally have very unusual material properties, and they tend to be mainly utilized for the industrial applications. They are used for serving as a controlled drug delivery has also been investigated. But again, they don't tend to show such straightforward results. So in this particular case, they show very unusual material properties, though they have very different material properties in comparison to others, which we will see in case later on. So we can see that then they form the nitrogen phosphorus bonds basically from the backbone, and they are mainly utilized for the controlled drug delivery, but they have been mainly utilized for the industrial application, not really as a biodegradable polymers into the body. And this is one of the very important classes of the biomaterials, which is called polyglycolic acid and the polylactic acid. This is one of the very initial synthetic polymers which have been developed, and now they have been retained as one of the primary biodegradable polymers which have been utilized very widely. And again, as we see that they are most widely investigated, as well as they are most commonly used as a bioerodible polymers. And again, we see that the PGA is a linear aliphatic polyester, and because of its linearity and aliphatic nature, it is highly crystalline, which actually increases its melting point to very high, 210 degrees centigrade. And because of its high crystallinity, its solubility is also very low in the organic solvents. So we can see that initial development which was there for the stable materials, these are one of the first class of materials which were biodegradable in nature, and after their approval it has become very hard, because these materials are so good that they have imposed very stringent requirements of biodegradation as serving as a biodegradable polymers into the body. So there are only three very widely used polymers, which are polyglycolic acid, polylactic acid and polydiaxanone, and among them polyglycolic acid and polylactic acid are one of the most commonly used bioerodible polymers. And again, PGA is a linear aliphatic polyester, as we see here. This is the overall polyglycolic acid what we see here, and again it is very crystalline in nature, and thus it has a very high melting point of 210 degrees centigrade, but it has a problem that it possesses low solubility in organic solvents. So that actually creates a problem in terms of processing it, because we need the material to be highly soluble in a particular organic solvent, so we can cast it into certain difficult shapes. But PGA is very crystalline, and that makes also it little more brittle. And again, we see that on the other hand, the polylactic acid is a chiral molecule, and it basically occurs in two stereoisomeric forms, which basically form 2 into 2, 4 morphologically distinct polymers. One can be stereoregular. It has two forms, which can be DPLA or LPLA, and they are semi-crystalline in nature. It can be racemic, which is D, L PLA, which is much more amorphous, and it can also be meso-PLA, which is being rarely used in the practice. And now coming to their overall properties, that since the stereoregular, the DPLA and the LPLA, since it is semi-crystalline in nature, it has a good mechanical strength, and because of good mechanical strength, it is utilized in sutures or orthopedic devices. On the other hand, the D, L PLA, it is amorphous in nature, so it can be utilized as a media for dispersing active species or drugs for drug delivery. So that is what we can see, that PLA, because of its different stereoisomeric forms, it can form four morphologically distinct polymers, and depending on its overall structure, like stereoregular, it is much more semi-crystalline in nature, so it can provide high mechanical strength, and because of high mechanical strength, it can be utilized as either the sutures or orthopedic devices, either as bone screws, which can impart much high or better mechanical strength, or it can also be racemic in terms of D, L PLA, and because of that, it can serve as a matrix for the dispersion of the active species of the drug, so that it can always release drugs very easily. So that is how the overall engineering has been done for this polylactic acid. Depending on the overall mechanical properties, it can be either semi-crystalline or amorphous, and based on that, the overall degradation of polylactic acid can be controlled in terms of serving a particular functionality, which can be either sutures, orthopedic devices, or even be drug delivery release. But again, the combination of PGA and PLA, it is one of the totally synthetic absorbable suture, and the problem with that is it tends to lose its mechanical strength over 2 to 4 weeks. So it basically degrades very quickly, and it can also be used in the internal bone fixation when we require a very low duration. So it is basically being utilized as a bone pin. And again, this particular copolymer is basically being utilized as a combination of PGA and PLA, and again PGA has a lower mechanical strength of 2 to 4 weeks. So to basically conquer that, the PGA will basically dissolve in 2 to 4 weeks. So that is the reason we add PLA to it, because PLA is much more hydrophobic in nature. So copolymer of PGA, it combines with the hydrophobic polylactic acid, and that reduces the overall hydrolysis of PGA. So we have PGA, it comes in combination of polylactic acid, which is much more hydrophobic, and that reduces the overall damage which is caused by the hydrolysis of PGA. So the overall dissolution can be much enhanced by more than 2 to 4 weeks. So PGA tends to dissolve in 2 to 4 weeks, and that can be being conquered by adding much more super hydrophobic PLA, and that basically sustains the overall or basically hinders or restricts the hydrolysis of PGA. So that is one of the first developed basically copolymer which is much more biodegradable. And again, to appreciate the overall strengthening or the prolonged mechanical strength with the addition of PLA into the PGA matrix, we can see the hydrophobicity of PLA is so strong that it will reduce the water uptake of the thin film which is being developed on the PGA PLA by only 2%. So the 98% of water is being basically not taken or being discarded. So with the addition of PLA, only 2% water uptake occurs for PGA for its hydrolysis. So now we can see the overall strength or the mechanical strength has now basically increased, or it is prolonged in time as well. So overall mechanical strength is now sustained for a prolonged duration of time, but at the same time there is no linear relationship of how PGA PLA will interact, and that will provide certain mechanical properties or physiomechanical properties. So there is no direct relationship between the PGA and PLA ratio which can easily predict the overall dissolution rate of this degradable polymer. But again we can see that PGA rapidly reduces crystallinity. So the dissolution of PGA will basically tend to reduce the crystallinity, and which will increase the hydration and hydrolysis. So basically we can see that the dissolution of PGA will again reduce the crystallinity, and which will start introducing much more hydration and hydrolysis. So people have seen that the 50-50 combination of PLA PGA basically degrades much faster than either PLA or PGA. So the presence of PGA causes much more reduction in the crystallinity, and which again increases the hydration and the hydrolysis, the loss of PGA. So it is much more faster when we have 50% PGA. So the 50-50 copolymer will degrade much faster than either PLA or PGA. That is one of the beauties of this PGA PLA, that the combination of this can be engineered in terms of rendering a biodegradable polymer which can dissolve at much faster rate. So either we can control the overall hydrolysis by adding much more of PLA, which is hydrophobic in nature, that reduces the water intake, or we can increase the PGA content in terms so that we can somehow engineer a particular degradation copolymer which can degrade at much faster rate than either of PLA or PGA. So that is the advantage of this, utilizing this PGA PLA copolymer. So we can have a degradation of PGA which can be either be 2 to 4 weeks, which can again enhance it by the addition of PLA to much larger prolonged time, or it can be even shortened by a particular combination of PLA and PGA to much shorter duration. So that material can degrade at much faster rate than either of PGA or PLA. Now there are certain mechanical properties out here. So that part we can see that we have this polyglycolic acid, because of its aliphatic nature we saw that it has a very high melting point, and because of that it is again tends to be very crystalline in nature. At the overall processing part also becomes much more difficult for polyglycolic acid, and again it has a low solubility in organic solvent, so that makes the processing very difficult. Then we have different classes of polylactic acids. So again we can see the overall glass transition temperature in which we can make it work about this temperature is around 50 to 60 degrees centigrade, and again the melting point is little lower than that of a polyglycolic acid. Its strength is also a couple of megapascals, from 20 to 50 megapascals. They have tensile modulus in order of a couple of gigapascals, 1 to 3 gigapascals, and they possess high flexural modulus in terms it has a much more flexibility. So that is basically that it can provide it much more good elongation in terms of fracture. And then we have again pH polyhydroxybutyrate PHB. Again we can see that it has a very low glass transition temperature, so it can be easily worked very easily. It has a melting temperature of 171, a tensile strength again approximately 36 MPa, and again it has a very high tensile modulus, but at the same time it possesses very high flexural modulus as well, and it provides a generic yield and the break percent elongation. And again with the caprolactone, it is a glass transition of -62, which makes it very brittle even at room temperature, because it makes it very flexible at room temperature. So that is the advantage of this caprolactone, that the glass transition temperature is below the room temperature. So at room temperature it is very flexible. The same case is with the hydroxybutyrate. The glass transition temperature is much more lower. So at temperatures higher than the glass transition makes the polymer much more flexible. So in this case the materials are very flexible, as we see, and again the break percent is very high, the elongation percent is very high, and again the polyanhydrides, they also show very high percent elongation, as well as the polyortho esters, whereas the polyamino carbonates, they show a glass transition of 55 to 69. The tensile strength is 40 to 50 megapascals, whereas the tensile modulus is again couple of gigapascals. And we can see the polyanhydride, they possess one of the very low tensile modulus. They are very flexible in nature, as we see here. So that is the overall deal with the mechanical properties of the degradable polymers, starting from polyglycolic acid, polylactic acids, polyhydroxybutyrates, polycaprolactones or polyanhydrides or polyortho esters, and the polyamino carbonates. So that is the overall generic properties of the materials, starting from glass transition, melting temperature, their elongation, flexural and tensile modulus, and the tensile strength. And again coming to the overall applicability part, we can see that the synthetic degradable polymers in terms of polylactic acid and polyglycolic acid, they have been widely utilized in the drug delivery or the guided tissue re-engineering, basically for the dental applications, as sutures, as staples, stents, also in the tissue engineering. Whereas the combination of polyhydroxybutyrate and the polyoxyvalerate, they have been utilized for the long term drug delivery, because depending on the combination PHB and PHV, they can provide a very long term drug delivery in comparison to that of PLA, and they have been also utilized as the orthopedic applications for stents and sutures. And again coming to the polycaprolactone and polydiaxanone. Polydiaxanone is again one of the very much utilized biodegradable polymer. It is basically utilized for fracture fixation in non-load bearing bones or sutures or wound clips. Polycaprolactone, it is being utilized for the drug delivery or staples, stents and orthopedic applications. And there are certain other synthetic degradable polymers such as polyanhydrides for drug delivery, polycyanoacrylates for the adhesives, mainly utilized as adhesives or for drug delivery, and polyamino acids or called pseudo amino acids for drug delivery or orthopedic applications. But as we know that because of their swelling, they tend to have very uncontrolled drug delivery rate. So that is the problem with them, and again they have very different. So that is the problem with them, that they have, first of all, on swelling they don't really tend to give up a particular drug delivery, and also they tend to because of their antigenicity and because of their insoluble nature, they basically are limited by their application. And then we have polyortho esters, because they can be utilized for the drug delivery or the stents. Polyphosphazines, they have been utilized for the blood contacting devices, drug delivery, or polypropylene fumarate for orthopedic applications. And there are other some natural resorbable polymers as well available, which can extend from gelatin, cellulose, collagen, starch and amylose, basically for various applications. So in the overall we can see that there are a variety of polymers which are available, which can be again controlled by a particular combination by making a copolymer, and that can be utilized for the drug delivery devices or for certain wound healing applications. And also depending on the mechanical property or physiochemical properties, they can be easily tailored depending on what kind of copolymer which can devise. And in comparison to the long term non-interacting polymers, the biodegradable polymers, they have to undergo very stringent requirements, because first of all the design part, they have to be designed properly so that upon degradation they don't really lose the overall structural integrity, and their overall release rate or the overall cellular response also has to be tested, and it has to be predetermined or pre-estimatable, that upon certain degradation rate, that will be the overall cell response. Otherwise it will lose the overall integrity with the surrounding tissues. So that there are certain issues which are basically related with that. So they have to be first of all in vitro tested, in vivo particularly established on animals, and there have to be certain clinical trials before it can be easily commercialized. So that is the overall deal with the biodegradable polymers. They have to undergo very stringent requirements of the Food and Drug Administration, and then only they can be commercially established. And depending on the applicability, PLA and PGA and polydioxanol, PDS, they have been widely utilized as the biodegradable polymers. They have been one of the very earlier ones which have been established, and later on, because of very stringent requirements, it becomes very tedious to undergo the same process of getting an approval and then using the new materials or newly developed biopolymers as a biodegradable polymer for the body implants or for any drug applications or any certain biodegradable applications in the body. So that is the overall deal with the polymers, that we can somehow we have to engineer them, and we have to undertake the design part, the testing part, and the overall aspect of what functionality it will render once it is inside the body. And with that, I will end my lecture here. Thank you.